Welcome to today's video. Today we're going to learn about curves, smooth curves in particular on manifolds, and we're going to talk about vectors and vector fields. So there's a lot to talk about because we remember working with our bag of infinite potatoes with something that is weird to do calculus on if you want, but then we have an atlas that is a set of charts that allows me to locally map this manifold, this bag of potatoes to Rn. Okay, this would be Rn if that's the manifold. This is representing the homeomorphism associated with some chart that covers the point x. So we have a point x here in the manifold, which is, the serifa x, and then through phi we assign coordinates x super mu equal to whatever the map of this x through phi is, so whatever phi maps x to in Rn. Okay, that's what we saw in the previous video. Now, let me define a curve on the manifold. What is a curve? Let's see. All right, so look at this. What is a curve? So a curve, let's first think about the intuition, is some sort of path in my bag of infinite potatoes. Okay, what is that? I mean, intuitively, it's just where I move from one point to another in my manifold in some particular way. Now, let's see. What is it exactly? Well, a curve, it's a function that goes from the real numbers, these are the real numbers, to the manifold. So I have a gamma of tau, and for every value of tau, I connect with one point of the manifold. Okay? So I can define an x that now depends on tau, which is a point in the curve, right? I mean, we've seen this many times. For example, you write parametrized curve in R2, for example, like this. So you have something like x of tau, cosine tau, sine of tau, right? This is x of tau. Well, this one is x of 0. This point is, let me write it like that. This point is x of pi over 2, etc., right? So you move, as you vary tau, you move in your manifold. In this case, it's R2, right? Well, this is the abstract notion of that. It's a function from the reals to whatever the manifold is. It's a function from the reals to my bag of infinite potatoes. Great. So the difference in this example with R2 that I gave you and the manifold is that, well, what does it mean to be a smooth curve? What is the notion of continuity of the curve, etc., etc., if we're talking about an abstract object that is my manifold, my differentiable manifold? All right, well, we can actually use this chart that we have to map it to Rn and see what we have in Rn. Of course, a curve gamma in the manifold can be mapped through phi. Every point in the curve x of tau can be mapped to Rn. And in Rn I get a parametric curve in Rn. The coordinates, this x super mu of tau, is the map of x of tau being every point. This is if you want, this thing here would be, for example, x of 0, right? And this is x of an arbitrary tau that I wrote here, right? A point x of tau gets mapped to a point x mu of tau in Rn, the coordinates of that point. And this, of course, I can run tau, and that will draw a curve in Rn. You see, this one is like pretty straight, and this one I didn't write it straight because here's a bag of potatoes, and this is in Rn. So this curve represents the mapping through the chart phi of the curve gamma. All right? Okay, so you can tell that there is a function x mu of tau, which are the coordinates under this chart of the curve gamma, and that function is the composition of gamma with phi. So first, take the reals, take them to the manifold, and from the manifold to Rn. So this function here is a function from the reals to Rn. And because it's a function from the reals to Rn, we have all the notions. We know if this function is smooth because we know what it means to be smooth in functions that go from the reals to Rn, right? So we can talk about a smooth curve if the function phi composed with gamma is a class infinity function. It's a smooth function. So there you go. You have a notion of smooth curve. Basically, a smooth curve is a map from the reals to the manifold such that when you compose it with the homeomorphisms coming from a smooth atlas, yields smooth functions from R to Rn, and this is a smooth curve. I hope that's clear. So I'm moving, gamma moves me as a function of things of this tau as a t. It's like you walking in your manifold, you're moving from potato to potato as your time increases. That's the tau here. So as I move in tau, right, then you see if this is tau equals 0, then that would be mapping to that point over there, right? As tau increases, I start walking from here to going around the curve in the manifold. And when I go through phi, it's the same thing. I start at here, for example, x of 0, and then I start moving as time goes by in Rn. This is the representation in coordinates, in local coordinates to the chart phi of the curve gamma of tau, or x of tau that comes from the function gamma mapping the reals to the manifold. I hope that's clear. So look at that. We have defined the notion of a curve, and a smooth curve for that matter, in the manifold, which is again a map from the reals to the manifold. All right, so now that we know what a curve is, let me introduce functions that go from the manifold to the real numbers. All right, so I define the function f as a map that takes me from the manifold to the reals. This is another copy of the real numbers, and a function on the manifold is something that maps points in the manifold to the real numbers. Now, okay, I can write it like this. So the same way the curve goes from the real to the manifold, f goes from the manifold to the real numbers. That's what we call a function. Now, what does that mean? How do I know what a function is? It's like smooth or not? How do I differentiate? You see what I mean? This function is unlike anything you've seen in calculus, because it's from a freaking bag of infinite potatoes and greens and babies and what, maybe I shouldn't say babies. This function is unlike anything you've seen before in vector calculus, because this thing is not Rn. This is a bag of fluffy things or something like that. This is a manifold. You don't know what it means for a function like that right away to be differentiable or continuous or smooth or anything. It's difficult to do calculus on this function, because if it were Rn, yes, I know how to do it. That's calculus, right? But if it's m to r, I have no idea how to actually talk about that other than it's a map. Luckily, my manifold has a structure of differentiable manifold through the atlases. So I have a chart, and I can use this chart to make sense of this function in the following way. I define a new function, f bar, which is the composition of f and the inverse of the homeomorphism in the chart that I'm using to translate to Rn. Now, look at that. What kind of function is it? What does it do? Okay, so phi minus 1 goes from the Rn to the manifold. So I start from x mu here, and from that x mu go to a point of the manifold. And then, now I apply f. Through that point of the manifold, I get mapped to R. So this new function, f bar, maps Rn to R. Nice, this thing is a function that maps, let me write it here, Rn to R. So this function, I know how to differentiate, I know how to do calculus with it, no problem, because it's a function from Rn to R. And because it's a function from Rn to R, I know that this, I can talk about smooth functions. I'm gonna define definition, a smooth function in the manifold is a function that through some infinitely differentiable atlas, through the translation maps, if you want, that take me to Rn, compound with the function, gives me a function from Rn to R that is smooth. So you see what we're doing? We are exploiting the fact that we have this correspondence locally from the manifold to Rn to define abstract objects that I have no idea what they are in the manifold through the things that we know, through the definitions that locally are in Rn, which is what we know how to do. This is the whole trick, the whole purpose of differential geometry. All right, this is kind of cool, like learn how to do calculus with potatoes through making a way to use the calculus that you know how to do, which is calculus in Rn, and then having a translator that takes me from the manifold to Rn. Okay, warning, in many books about following physics, but even in some math ones, they abuse a lots notation and f bar. They don't distinguish f bar from f. Of course, they're different objects though, so be careful. In this course, we're going to distinguish f goes from the manifold to the reals, f bar goes from Rn to the reals. So this thing is equal, f of x with the serifas is of course equal to f bar of x mu. All right, so the value of this function of this point is the same as the value of f bar on the coordinates of that point. All right, which is a point in Rn. Going back to the notion of the curve, so I did it for a generic point x, but that could be done, of course, by I can map with f every point in the curve, right? So I can have it like this. Right, so if we consider that we are moving along a curve, I can consider, for example, what is the value of the function along that curve. So I evaluate f over the point x of tau, right, with tau varies in the manifold, and that takes me to the real, and that's the composition of gamma and f, right, of tau. So this composition of gamma and f that I have here is a function from the reals to the reals. The composition that I have here, this thing is, let me just write it here, composition of f with gamma is a function that goes from the reals to the reals. Right. Now, we can have a translation on Rn by using f bar. It's the same, this is exactly equal. How do I know? Well, f composed with gamma starts here in tau, that goes to the manifold and then takes me to this point. Is this the same point I would get with this one? Well, let's see. F bar of x mu. F bar of x mu takes the point x mu that comes from x, right? And it through f bar takes me to the same point. So indeed, they're exactly equal. This thing, this function, this as a function of this as a function of tau, this f bar of x mu of tau as a function from this tau, the reals, to the outcome of that, which is the real, is the same function as f. Okay? Now, we can use that to express it in this form. I know that the function f of x of tau, the function that takes me from points in the curve to here, is the same as the function f bar of x mu of tau, the function that takes coordinates of the point in the curve and takes me to the reals. All right. Now, this is something that we know very well, because this is a function from Rn to R. We've seen those. It's a real function. It's like, for example, I don't know, you've seen when you're running physics, the potential, right, of something. Well, the potential function here is a function that takes points in Rn and returns a scalar, returns a number, right? In fact, we're going to call the functions the scalars, but let's not get ahead of ourselves. You know, this is exactly what we have here. We have a function of some vector of action. We have a function of some point in Rn and returns a real number, right? So it's like this function. There's nothing very difficult. In particular, you want to, what is the potential? Let's say the electric potential that I feel when I walk along a curve. Sure, that would be a function of your trajectory. That is a function of time, the parameter you use to walk. All right, but this is exactly the same here. So this is, if you want, sure, this is v of x of tau, y of tau, z of tau, right? If it's three-dimensional space. Same thing, x1, x2, x3 to xn are the coordinates of the point x through the map phi. All right, wonderful. So if this function is a function that I know how to differentiate and so on, I think I would be able to make sense of the following. I can ask, what is the variation of the function f as I move in the curve? Does that remind you of something? That's the notion of directional derivative that you have from calculus. As I move along the curve, I look at the variation of the function f. As I move in my room, I look at how the electric potential changes. So that's exactly what I want. I want to know the change of the function f, the rate of change of the function f, as I move in the curve. So what I want is the derivative with respect to tau of f compound with gamma. All right, so this function here. How does the function f compound with gamma vary as I vary tau? As I move along the curve, how does the function f vary? All right. But then I know that the composition of f with gamma is exactly this. So I know that this thing would be equal to the variation with respect to tau. This function is a function from the reals to the reals, and this one is exactly equivalent to the variation of f bar x1 of tau, x2 of tau, x3 of tau, right? And I truly know how to compute that. I can compute that using, of course, the chain rule, right? So I know that this thing, so the variation, this thing is going to be equal to the partial derivative of f bar with respect to x1, and then the variation of x1 with respect to tau, right? Evaluated, say, at the point tau 0. So let's say that I'm at point tau 0. Let's say that I want to evaluate this derivative at the point tau 0. Okay? So we continue, and that will be now plus the derivative, partial derivative with respect to f of x2, f bar, d x2, d tau. evaluated at some point tau 0, plus etc., right? The sum of all of them. In fact, we can compactly write it in index notation the following way. The derivative of, with respect to tau, of f compound with gamma at the point tau 0 would be equal to, and then I write this is an Einstein sum, you see, so this is going to be partial mu f bar contracted with the derivative with respect to tau of the coordinate x mu, right? This symbol partial tau here signifies derivative with respect to tau, okay? Even though I wrote partial, is what I should write. Don't be confused by that. It's if you want a total derivative in that sense, but I write the sign partial for a reason. Anyway, partial tau means here derivative with respect to tau of x mu, and that multiplied by the derivative with respect to the coordinate x mu. Remember the notation, right? When I write partial mu, I'm saying that this is the same as writing partial x mu. All right? So if you expand this Einstein sum, you get exactly this expression. All right. Well, right. The only thing is that I want to evaluate at the point of 0. All right, so everything is evaluated at the point of 0. Wonderful. This is, I just defined the variation of the function along the curve. But you see, this is the key, and this is abstract, but it is important. I am about to define vectors in the manifold. And you're like, what? And I'm like, yeah. How? For a vector, you need some notion of direction or something like that. But this is potatoes. There's no notion of direction in this fluffy thing. Yes, but there is. Because I can move in a curve. And moving in a curve with the parameter tau, walking some path, is giving me a notion of direction. And now I can define vectors in the manifold as the tangent vectors to a curve. I can define a vector as an object that is the tangent vector, the object that gives me the directional derivative of functions when I move along the curve. So let me work a little bit with this in order to define vectors. All right, so I just copied the formula that was here up here, and basically say, okay, the derivative with respect to tau, right? So the parameter of the curve, remember that tau is the parameter of the curve that tells me how to move around the curve. The derivative with respect to tau of a function f compound, of course, with gamma, meaning that is along the curve. I move around the curve and I want to see how this f changes along the curve. And all that I did in this step is just to switch the order of the two terms, right? This one was last and this one first. Now this one is first, this one is last. I actually don't need to write the x of tau 0 here, but because I didn't write it here, but I could have written it and I'm just explicit in there. Everything here means evaluated at tau 0, and that means, of course, evaluating the partial derivative of f bar at the point x mu of tau 0. So this would be x mu of tau 0, right? If you want, I can add it here. I didn't write it here, but let me add it. So you see that that's not different. So this is the way in which you take the derivative with respect to tau as you move along the curve of a function. But now you can say, okay, fair enough. If I want the direction, if I want to define a notion of direction, just give me the operator that takes the derivative of the function, the operator, like a differential operator. Like you remember, like the gradient multiplied by the direction in calculus. Give me an operator that takes the directional derivative in the direction of this curve of any function that I plug in. How do I build that? Well, that's easy. Just erase the f from here. Leave a blank, leave a blank, leave a blank here. This is what I'm going to do. I'm going to take the operator that computes the partial derivative, what I call here partial t, computes the derivative of the function in the direction of motion in the curve. So this thing, if I write here, would be, using this one, would be partial tau x mu, all right, evaluated at tau 0, contracted with partial mu, the partial derivative with respect to x mu. And now you say, if I act with this operator on a function, if I get v, this v that I define, acting on a function that returns the derivative with respect to tau of the function component in the direction of the curve that the tau is parameterizing. So that's exactly what we want. This operator, this is the definition of vector. you see, that's the direction, the definition of vector. A vector in a differential manifold that generalizes all the vectors that you've ever seen before. The vector that I'm defining, this vector that I'm defining here, is the tangent vector to the curve gamma. That's how I define a tangent vector to a curve. The tangent vector to the curve gamma, which represents the derivative with respect to the parameter of the curve tau, it's defined as this operator. Insert here any function and it will take the derivative that I'm talking about, the directional derivative of the function as I walk along the curve. How does the potential or any function that I put in will change as I move along the curve. And now you see something very interesting. This vector is a linear combination of stuff, right? In particular, you can think of, remember how a vector in our algebra introduction, you wrote a vector as some component and then some element of the basis. And let me write the elements. In the past, I've written elements of the basis like this probably, or like a calligraphic one. Let me call them epsilon here, okay? So you remember there was a basis, right? A basis epsilon mu, right? And that base of vectors, as a vector can be written in terms of a linear combinations of elements of the basis. Well, very similar here. Look at what we have. This thing, as we write here, is some number, some coefficients. This is a sum, this is an Einstein sum, remember? So these are the coefficients that accompany the partial derivatives. And the partial derivatives are certainly taking derivatives along some direction. The direction of what the axes represent, right? The coordinate curves under this chart. There are some curves in here that represent the x-axis. When you chart them, one coordinate here represents one curve here. Maybe this curve represents the x-axis when I map it with the chart phi. This one represents the y-axis, and this one represents the z-axis, and they get mapped with the chart phi into the coordinate curves, right? This is exactly what these partial mu operators represent, the tangent vectors to the coordinate curves. So the tangent vectors to the coordinate curves are exactly the elements of the basis of vectors that we can use to build any vector that is tangent to the curve gamma at a point gamma of tau 0. So this definition is the tangent vector to the curve gamma at the point gamma of tau 0. Now this is super interesting. So partial derivatives in some direction, be it the coordinate curves or be it an arbitrary direction, this action. So first thing that we have, these partial mu's represent vectors. They are vectors. Partial derivatives are vectors. Well, vectors are directional derivatives, and in particular, partial derivatives are directional derivatives in the direction of the axis, right? Of the coordinate curves, you would say. In the manifold, there are coordinate curves that will translate into the axis through the map chart, through the map phi. So, wonderful. Thing that we learn now, thing that we just learned. Vectors are derivatives. And in particular, the partial derivatives are vectors. So if I write partial 1, which means, remember, it's partial x1, that's a vector. And it's a vector in the direction of x1, if you want. It represents the vector here. It represents the vector here that is tangent to the coordinate curve that would give rise to the x1 axis. All right, this is abstract, but I hope you can follow it and that you have questions. But important, we've established that the vectors are derivatives. You can write the vector as an expansion, as a sum, right, of coefficients and elements of a basis. And we saw that the partial derivatives are bases for the space of vectors, tangent vectors of a curve at a point. So qualification, to be completely rigorous, even though this is done everywhere, but to be completely rigorous, let's distinguish a tiny bit between the abstract vector epsilon mu. The abstract vector epsilon mu will be the vector tangent to the coordinate curves. And that thing, how does it add on functions? So, well, if I act with epsilon mu on a function f, remember a function in the manifold, from the manifold to the reals, at a point x in the manifold, this thing is going to return to me the partial derivative with respect to partial derivative mu of f bar at the point x mu, the coordinates of the point x in the manifold. So it's important, even though we're going to say that this is a vector and there's an identification between these things, and we're going to say it all the time, epsilon mu is the abstract object that takes directional derivatives in the direction of the what we call the coordinate curves in the manifold, and a partial mu takes the derivative, if you want, the partial derivative with respect to the direction of the axis that represents that coordinate curve in Rn through the chart phi. But it's often the case that we just say that partial mu is the vector as well. So very important, vectors are derivatives. And as such, they will satisfy the Leibniz rule. Okay, let's talk a little bit about vectors and let's define the notion of tangent vector space. Okay, a little plot just to help solidify the notion of coordinate curve. What are the coordinate curves? Well, they are the curves in the manifold. This is the manifold that when mapped through phi, all the points of them, they give you the axis on the particular Rn that this phi maps to. Okay, so you can tell that in the abstract manifold, for example, epsilon1 will take is the vector that takes the directional derivative of any function f in the direction of this curve, and here it would be just the partial derivative with respect to x1, right, which is this axis. All right, so I was saying that vectors are derivations, so satisfy the Leibniz rule. That means that if I apply two functions, this is satisfied, which is Leibniz rule. All right, let me define the notion of tangent vector space. We define the tangent vector space that I notate. This thing means this is the
tangent vector space to M at P, which is the point of M.
The tangent vector space to M at the point P, TPM, is the set of all the vectors Vp. P notates the point of the manifold in which I'm defining this tangent vector space. This is a vector space of the same dimension as M. And the set of vectors, epsilon mu, that are, remember, the vectors tangent to the coordinates curves associated with this chart, so the ones that generate the axis, form what we call a coordinate basis of TPM, so that I can expand Vp in terms of elements of that basis. Now, keep in mind that you can have a non-coordinate basis, and we will talk about that. In fact, the notation, I'm going to use Greek subindices for coordinate basis, and I'm going to use Latin subindices for arbitrary basis here. But we're going to talk a little bit about these coordinate bases. Coordinate bases can be associated with coordinate curves, with tangent vectors to coordinate curves, the typical partial derivatives that are independent from each other in your calculus. So this is nice because then I know if these things are partial derivatives. Imagine that I have now two different sets of coordinates. I have two phi's, phi and phi prime, so I have the set of coordinates x and x prime. So how do I change coordinates? What is the change of coordinates? What is the, if you want, the equivalent to the lambda that we have in special relativity, to change the components of vectors in one basis to the components of vectors in other basis, or change elements of the basis? If you remember from our video, our second video, elements of the basis and prime to elements of the prime basis. How do we establish change of basis? Well, knowing that these are partial derivatives, it becomes rather easy, right? Because I know how the partial derivatives are related, right? The partial, if I have two set of coordinates, I might have again two phi's, so I have coordinates unprimed and then prime coordinates, two different sets of coordinates. How do they relate to each other? How do the derivatives relate to each other? Oh, I'm so sad I cannot ask the class, because I know the class knows that, because you know your calculus. The relationship between the derivatives in one coordinate system to another coordinate system is what we call the Jacobian matrix. So the matrix of change of basis between elements of the base, of course, remember what this is. This expression is, let me just write it completely. So it's partial x prime mu equals something, mu nu, partial x nu. That's exactly the same as that, right? That's the abbreviated notation for that. Well, I know how that is. This thing has to be, for the two things to be equal, the dirty math physicist trick to remember is, I need to have the x nu on top and the x prime mu at the bottom, and that acts on partial x nu. And then the dirty physicist trick, very dirty by the way, is saying, right, this would cancel that, and I end up with the partial derivative with respect to x prime mu, right? So I know what the lambda is. The lambda is this thing. The lambda that I have here is nothing. I'm going to write it here. Lambda mu nu, the change of basis, the change of basis, change of coordinate basis in the tangent vector space is nothing but the Jacobian matrix. Partial x nu, partial x prime mu. A matrix made of derivatives of the old coordinates with respect to the new ones, as you build in your calculus courses. So this is nice because then I know these things are representing the same objects as this one are, only one in the Rn picture, the other one in the manifold picture. So indeed, prime mu associated with one coordinate basis relates to another coordinate basis through the Jacobian in the same way, right? Where this thing is the same Jacobian, so it's the same matrix exactly. Wonderful, so now you know how to change bases. This is the kind of thing that we've been doing in special relativity without telling. We know how to change bases, coordinate bases in the tangent vector space to a point in the manifold, which is where vectors live. Now you know what the vectors are in the manifold. In Rn, usually you just draw the vector and say, oh, this is a vector, but what you're really doing though is thinking of the tangent vector space to Rn in that point. Only so happens that it's exactly Rn in Rn. So in Rn, everything is simple and trivial. But it's not true in a sphere, for example. How you define vectors over a sphere? Well, you think of the tangent planes if you want, and you have a vector tangent to the sphere, right? So this is what we're doing. We're generalizing to beyond the sphere. We're going to bag of infinite potatoes, or space-times, or friendship, or whatever you want. That's what we're doing here. How wonderful. All right, so quick question. If the elements of the basis transform with Jacobian, how would you think the components of the vectors transform? Let's call v prime mu transform under changes of basis. So I have here the v nu, right? The components of the vectors. Well, of course, we know it already. They transform with lambda tilde. So that would be lambda tilde mu nu, right? And that lambda tilde is nothing but the inverse transpose of the Jacobian matrix. If we write its expression, mu nu, it would be just inverting these two, okay? So we have partial x mu, partial x nu. All right, so we know now the change of basis matrices, which are the Jacobian and the corresponding tilde version of it, that change from elements of the basis to elements of a different coordinate basis, and from elements, we change from elements of a coordinate basis to elements of a different coordinate basis through lambda, and then we have the components transformed with the lambda tilde. So vectors are what we call contravariant objects. We call them contravariant vectors if you want. And again, as usual, they have the components have index upstairs and the components transformed with lambda tilde. It's very similar to what we saw in the algebra version of this. Only that we're doing now with infinite potatoes. Okay. Now, next thing. Right, so a vector field, what is the definition of a vector field? A vector field over the manifold M is a set of vectors of the tangent space TPM per each point of the manifold such that the components of that vector field in any coordinate basis are smooth. Right, what does that mean? Well, the idea to think of is the following. Imagine the electric field in this room. So the electric field in this room, you have a vector at every point in the room, and as you move, the vector changes because the electric field changes, but it changes in a smooth way. That's kind of the idea. So I get an element of the tangent vector space at every point in the manifold. So the tangent vector space at every point is a different tangent vector space as I move. Imagine that I move along a curve, gamma, and as I move, I pick elements of the tangent vector space here, and the tangent vector space here, and the tangent vector space here, so that the components of those vectors, as a function of tau, the parameter that I move in the curve, is smooth in all coordinate bases, in all possible coordinate bases. So again, it's analogous to defining, okay, the gravitational field in this room at every point is different, but you go smoothly from one point to another. It doesn't suddenly jump like that. All right, so that is a vector field. Now I have something written here, we will see in a minute what it means, but first of all, let's focus on the following notion, which is very interesting. Now, of course, a vector alone gives you a directional derivative. So if I apply the vector to the function f, I get a number, the directional derivative at the point in which I am in the tangent space to that point in the manifold, and that vector gives me the directional derivative in the direction of the vector at that point in the manifold. However, if V is a vector field, then at every point in the manifold, this is going to be a different number. So in a way, it's the directional derivative of something, is the directional derivative of a function defined in the whole manifold, but at every point in the manifold in different directions, according to what the direction that is every element of the vector field. At every point, the vector field is pointing in different directions, so it gives me different directional derivatives at every point. So this thing is in itself another function, right? Because it's a numerical value at every point, but I have a different vector at every point. So a vector field acting on a function is a function itself. Okay? Wonderful. So we can wonder now whether the composition, you can compound two vectors and you can compose two vectors, since v of f is a function, I can apply now another vector w on that function g, which is the vector applied to the function, and this vector will give me a number. And if this vector is a vector field, this will itself be another function. Now, I'm going to be abusing language in the rest of the course, and every time that I say a vector or a tensor or a form or something like that, I'm going to be talking about vector fields or tensor fields, all right? I'm not going to be referring just to vectors at a point and the tangent vector space at that point. I'm going to be talking about vector fields. So from now on, I will not say vector fields all the time. I will say vectors, and I mean vector fields, okay? Unless I say the opposite. Now, one thing that we can wonder is, right, is the composition of two vectors a vector? So now that I know I can compose vectors because vector fields, is the composition of two vector fields a vector field? Well, that would be cool. Let's see if it is. So I have here the composition of the vector field v and the vector field w, and I act on the product of two functions. What do I get? Well, first, Leibniz rule, right? Because it's the vector w is a derivative, so Leibniz rule. W acting on f times g plus f times w acting on g. And now the linearity of the application of the vector gives me that this is what I would get. And now I can apply Leibniz rule again. So if I apply Leibniz rule again, I get this expression here. And then I can rewrite everything in terms of v composition with w, which is, this is v composition with w, f times g is will be this term, right? This is this term. Notice how I try to separate. When I write dot, it means a regular product, and I do a circle for composition. Make sure, because otherwise the notation could be a bit cumbersome, right? This other term, f times composition of v with w acting on g, is exactly this one, right? And this one is this one, okay? Literally the same without manipulation. Does this satisfy Leibniz rule? Does the composition of two vector fields satisfy Leibniz rule when applied to two functions, the product of two functions? No. I mean, almost. This thing does satisfy the Leibniz rule, but this thing doesn't. This thing spoils it. So, not Leibniz, right? So the composition of two vector fields is not a vector field. Sad. So yeah, that's not the structure of vector fields. You cannot make another vector field by composing two vector fields. But maybe there is a way, a new rule or a different rule to compose, to take two vector fields and create a vector field that actually works. And if it works, maybe it will reveal something fundamental about vector fields. Now let's see. If it were this alone, it would satisfy Leibniz rule. It's just this stuff that spoils it. Can I get rid of it? Yes, let me define an object. Okay, so I define this bracket operation that takes two vector fields and action. Well, I define now this bracket that takes two vector fields and returns this. And this is v composition with w minus w composition with v. Let me show you its features. This is particularly nice because if I now apply, bracket of vw, right, to the product f times g, what do I get? Well, first of all, I would get I would get something very similar to this. I would get f times, and now I would get here v composition with w minus w composition with v, right? Acting on g plus g times composition of v o w minus w composition with v acting on f. And what about the rest? Well, this thing, you can tell the first one will give me something exactly like that, and the second one gives me exactly the same thing but with a minus sign. So this part cancels when I evaluate this object. Isn't that wonderful though? That's really wonderful because this thing is satisfy the Leibniz rule. So what we get is that this bracket, this bracket operation of V and W is something that is linear and satisfies Leibniz rule. It is a derivation, it's a derivative. So this thing, it is a vector field. It is true that V composed with W is not a vector field, but the bracket like this of V and W is a vector field. Now, this bracket has a couple of properties that are of particular interest. It is bilinear in both arguments, bilinear, which means linear in both arguments. It's antisymmetric, of course, and satisfies Jacobi identity. Now, you may know what these three properties make out of it. We call this bracket, if you're a mathematician or a physicist, you call it a Lie bracket. If you're a physicist, you also call it a commutator. So the Lie bracket between these two vector fields, right? So this bracket that I defined is indeed a Lie bracket, satisfying all this. And it's so nice because the Lie bracket of two vector fields happens to be a vector field. And that is really nice. That means that the vector space of vector fields, together with the Lie bracket, form a Lie algebra. And this is kind of cool because the Lie algebra is the same thing that we talked about at the beginning with the generation of translations and so on and so forth. Remember? Elements of a Lie algebra generate operations of a Lie group. So vectors in the manifold are going to allow you to do things like moving around or follow the flow of the vectors, as we will see better when we see diffeomorphisms a little bit later in the course, in a couple of videos. Now, this is kind of cool in any case because it reveals that vector fields have an internal structure of Lie algebra. And this also tells you that learning Lie algebras and Lie groups, it's important for a physicist. Lie algebras are in quantum. When you take the exponential of some self-adjoint operator, e to the I, ht, or things like that, what you're doing there is you take an element of a Lie algebra and creating an operation of a group. Learning Lie algebras is important for mathematical physics and for a better understanding of almost everything. Mechanics, definitely quantum mechanics, and general relativity. So I encourage you to learn some Lie algebras, not necessarily in this course, this is just a notes that will be helpful, but nothing that you need to know from before. But I think hopefully that piques a little bit your interest about these topics. Now, let me give you a little exercise that I will solve, but I think it's good practice as well. It's something that I could have asked any of you. What are the components of the Lie bracket of two vector fields? Concretely. Alright, so prove that in a coordinate basis, the components of the commutator of two vector fields are given by this expression. These are the components. So this vector, the commutator, the Lie bracket of two vector fields is a vector field in itself, and the μth component of it is given by this expression. And of course, V mu and W mu are the components of the vector fields V and W, respectively. Alright, pause and try it yourself. And then I'll solve it. All right, so hopefully you tried it and you got it. In any case, let's do it ourselves. So we're gonna substitute V and W. I'm gonna compute the bracket of V and W. And I'm gonna substitute V by this expression in the coordinate basis. Remember, I can write partial derivatives here because it's a coordinate basis. Remember that a coordinate basis, epsilon mu, right, is associated with coordinate curves with the axis, and there are partial derivatives. You can represent them as partial derivatives equivalently, right? So, because what they do when they act on functions is take the partial derivatives, all right, on f bars, right? Okay, so let's see what we get. So I get here v mu partial mu, and then I get here w mu partial mu. Okay, maybe I can use a different index for this one. No. Or it's a dummy index, I can use whatever I want. Okay, what do I get? So when I apply that, I get the following. I get here that this is gonna be v mu partial mu w nu partial nu minus w nu partial nu v mu d partial mu. Okay, wonderful. All right, so this is a very basic exercise, as you'll see, because all that I need to do is choose wisely the name of my dummy indices. This expression, which one should I change? To have this one, I want nus in the v's. Okay, so I'm going to change the dummy indices here. This thing is exactly the same as v nu partial nu w mu partial mu, right? All that I did is changing the dummy variable mu, I call it nu, and the dummy variable nu, I call it mu. There are sums, I can call him Joshua if I want. This is something that the first time that people actually play with these things sometimes struggle. So think about it properly. I can do that. And if you don't see it, please discuss it with me. All right. All that I did again is change the dummy variables. I changed them to a different name. And then I write here, this I don't touch, nu partial nu, v mu partial mu. All right, wonderful. What does that mean? Well, that means that I can take the mu as the partial mu as a common factor, which is v nu partial nu, w mu minus, put it like that, w nu partial nu, v mu partial mu. Okay? But what is this? This is exactly the vector v in the basis partial mu. So indeed, you remember that any vector, let me call it u, you can write as u mu element of the basis mu. If you write in terms of partial derivatives, u mu is a coordinate basis, right? You can write like that. And these are the components. So certainly these are the components. That object here, how many labels are there in here? Only one, mu, because these other two are contracted. These are the components. And this is exactly this, right? The muth component of the Lie bracket of two vector fields is exactly this, which we proved what we were asked to prove. Very easy exercise. All right, very easy, but if you haven't done these things, it's the kind of exercise you need to do. I hope that it was all clear, and please do bring your questions to the live sessions. And this is all for today. We talked about, remember, functions in the manifold, curves in the manifold, then vectors and tangent vectors as the way to define vectors in your bag of infinite potatoes in your manifold through tangent vectors to curves. Then we talked about the tangent vector space. We talked about vector fields. We actually showed that vector fields have a structure of Lie algebra. And we have done a little tiny exercise to compute the components of vectors. Now, I hope that you understand vectors now in a manifold. They are defined through curves and tangent vectors to curves, right? Isn't it impressive that we can define things like vectors in something that is nothing like Rn? Maybe locally is like Rn, but it's not Rn, it's something very different. Yet we were able to define vectors, making use of the differentiable manifold structure that we had. Now, the next step is to define the covectors. Remember from your algebra, the things that have, the components have indices down, if you want to remember that. That's going to be defining the one forms. We will talk about that in the next video. Until then, take care.